So what you just saw there was a representation of the Rolle's theorem, which is a very, very special case of the MDT. Basically what you saw, beyond Maddie and Katie's ridiculousness, was basically Maddie and Katie starting at the same point and ending at the same point. And so if this is the case, then the Rolle's theorem states that somewhere in between A and B, the slopes must be equal to 0. So basically, if f is continuous on closed interval a to b, and f is differentiable on open interval a to b, then there exists, then f prime of c is equal to 0, which is this. It's the same! Yay, the slope of the tangent line is equal to 0. So that means that somewhere in the middle, if Maddie and Katie started at the exact same point, and then ended at the exact same point, then somewhere in the middle, they had to have been going the same speed. And you could see it on the Ridiculous Slow-Mo video, where they kind of caught up to one another. Maddie caught up to Katie, and then they ended up finishing at the same time. So that's the Rolle's theorem. It's pretty straightforward. Okay, so now what we're going to do is we're going to take Rolle's theorem, and we're going to try to apply it in regular everyday math instead of just abstract concepts. So this question is going to be asking, is the Rolle's theorem applicable when this function is on this interval? So first what we've got to do, this function is continuous everywhere except -2. Dum dum dum. But look, it doesn't matter because -2 is not on our interval. So, hooray! So now what we're going to do is we're going to plug in our numbers here for our interval. So it's going to be -1 squared minus 2 times -1 minus 3 all over -1 plus 2. And the numerator, after some magical math, is going to be equal to 0, making the whole thing equal to 0. So now we're going to plug in 3, so it's going to be 3 squared minus 2 times 3 minus 3 all over 5 is going to be equal to, well, the numerator is equal to 0 again, so the whole thing is going to be equal to 0. So there we go, we've proven that part of the Rolle's theorem. So now we're going to do some magical math. It's going to take a long time, so just skip to the next video. So because I've got a lot of other fun stuff to show you, I decided to just go ahead and do the work off camera and then basically explain it to you because it takes a long time for me to write. So after some quotient rule magic, we end up getting this as the answer to our quotient rule. Simplifying magic, here we go. It ends up giving us this quadratic formula, which we then solve using the quadratic equation, which gives us the answer x equals -2 plus or minus root 5. And since -2 minus root 5 is not on our interval of -1 to 3, then it has to be the second answer. And so this second answer is guaranteed to have a horizontal tangent. So yeah, that's what Rolle's theorem can do for us. It's pretty great, but it's also really easy. So I'm about to show you some more complicated stuff that I'll explain after you see this video. But I'm about to show you some more complicated stuff, specifically how the Rolle's theorem was used to prove the mean value theorem. Okay, so some preliminary stuff before we get started, because I'm going to need a lot of space to explain the proof. So what we got here, this is the MDT. So if f is continuous on closed interval a to b and f is differentiable on open interval a to b, then there exists a c on a of b such that f prime of c is equal to f of b minus f of a over b minus a. And here is the Rolle's theorem, which is all of this. It has to satisfy these conditions. But f prime, instead of equaling the slope of the secant is equal to 0, basically. And so it's equal to 0 as well. And so it's a really, really special case of the MVT. And so you can see the MVT, the graph we have for this MVT right here, is just if you rotate the Rolle's theorem, you just go like, then you can see that basically it's the same graph, just rotated just a little bit here. Oh, that was my finger. I'm sorry, guys. I can't videotape. So yeah, that's what that is. Just had to get that out of the way because, like I said, I'm going to need this whole whiteboard. Get ready. Okay, so this is now going to involve a lot of subbing in, so try not to blink here because it's a little more complicated, but nothing we as juniors who are taking calculus cannot handle. Look at us. We're so brilliant. Okay, so what's going to happen is we're going to use the point slope formula to help us out. So we're going to define g of x to be y minus f of a is going to be equal to the slope of the secant line, which, as we know, is f of b minus f of a all over b minus a. And that's going to be multiplied by x, which is regular x, minus a. Since our y value is f of a, then our x value is just going to be a. Okay, so the next thing we're going to do is we're going to create a little new function here. So we're going to say let h of x equal f of x minus g of x. And so we're going to say that h of x is basically the difference between these two functions up here. I know it seems like we're arbitrarily naming stuff. We kind of are, but it's really to prove the point and to get the MVT proved by Rolle's theorem, okay? So we're trying basically to take a function and help it to prove the Rolle's theorem and satisfy the Rolle's theorem, and yet also stay true to f of x. That's the point. It's going to help us out. So now what we're going to do is we're going to say h of x equals f of x, and since we've already defined g of x up here, we're just going to plug in g of x. And so we're just going to say over here, we're just going to move the f of a over. And so it's going to be f of x minus f of a plus f of b minus f of a all over b minus a times x minus a. Okay, so it's pretty easy. We just subbed in g of x. Just subbed in what that was. Okay, so now what we're going to do is, according to the Rolle's theorem, we can say that h of a is going to be equal to h of b, which is equal to 0. We can also, so here we go, so we're going to do h prime of x is going to be equal to, we're going to differentiate this whole thing, okay? So it's going to be, so this constant right here, right, over here, a is going to be equal to 0 when you differentiate it. X is going to be equal to 1, so it's just times 1. And then this is going to differentiate to 0 as well. And then we're just going to keep our regular one. So we have the h prime of c is going to be equal to f of b minus f of a all over b minus a. It's pretty cool stuff, right? So now we're going to say, also based on the Rolle's theorem, that h prime of c is equal to 0, right? Because f prime of c is equal to 0. So we're going to do h prime of c is equal to f prime of c minus f of b minus f a all over b minus a. Okay, so now we literally just have to move the f of c over, and then you get your final equation that we wanted for the MVT, which is f prime of c is equal to f of a, or f of b minus f of a all over b minus a. So I know I ran out of room there at the end. Told you it was going to take a lot of room. So there you go. So just to recap again, we took our point and slope formula, we plugged some things into that, we just defined a new function there, the difference. Then we just differentiated that, got our answer there, h prime of c, and there we go, right there at the end. We have proven the MVT using a really far easier function, or far easier proof, the Rolle's theorem. So there you go. Job done.